So the question is, how many of these molecules are polar? To do this, we're going to take each molecule and first draw the Lewis structure, then draw the bond dipoles using the electronegativities of each atom in the molecule, then identify the molecular geometry to find the net molecular dipole. And if there is no net molecular dipole, then the molecule's bond dipoles cancel and the molecule is nonpolar. If there is a net molecular dipole, then the bond dipoles don't cancel and the molecule is polar. So for the first molecule, we're going to draw the Lewis structure. This molecule has 24 valence electrons, so the first thing we're going to do is make octets on all the outside atoms. So when we count the electrons, there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've used all the valence electrons, but S still doesn't have an octet. So we're going to have to create a double bond between one of the O atoms and the S atom. There could be 3 possible Lewis structures for this molecule, meaning that it has resonance, so the actual molecule will be a resonance hybrid with 3 identical bonds. But for this problem, we're just looking at the domain, so we don't really have to worry about that. So now we're going to draw the bond dipoles, but first we have to determine the electronegativities of each. So O has a higher electronegativity than S, so it will have a partial negative charge. And the S atom will have a partial positive charge because electrons drift to the more electronegative atom. And now we're going to draw the bond dipoles, which move in the direction of the negative. The central S atom has 1, 2, 3 domains and no lone pairs, so the molecular geometry is trigonal planar. And it would look like this. In a trigonal planar molecule, all the domains are the same, so the bond dipoles will cancel, and there will be no net molecular dipole, which means that the molecule is nonpolar. So we can eliminate this one from our answer. So for our second molecule, I wrote the Lewis structure, and it has 20 valence electrons, and all of the atoms have an octet. So drawing the bond dipoles, first look at the electronegativities, and F has the highest electronegativity, so it's going to have a partial negative charge. And the O is going to have a partial positive charge. And the bond dipoles will go in the direction of the negative atom. So looking at the bond dipoles, it looks like they would cancel out, but we have to look at the molecular geometry to make sure that's true. So the O atom has 4 domains with 2 lone pairs, which is bent geometry, molecular geometry. So in the bent geometry, this is what the atom would look like, or the molecule would look like. And the bond dipoles are pointing this way. And just by looking at it, you can see that there's a net molecular dipole in the downwards direction, which means that the molecule is polar. And also, in bent geometry, not all the domains are the same, so that's another way to see that there is a net molecular dipole and that the molecule is polar. Now looking at the third molecule, we can see that it has 16 valence electrons. So we start off putting octets on the outside, and we used up all the valence electrons doing that, but it's okay because Be is an allowed octet violator and can have less than an octet. So it's okay with having 4 valence electrons. So to find the bond dipoles, we look at the electronegativities, and Cl has a higher electronegativity than Be, so it's going to have a partial negative on both sides, and then Be is going to have a partial positive. And the bond dipoles will point towards the more electronegative atom. So once again, it looks like the bond dipoles would cancel and the molecule would be nonpolar, but we have to look at the molecular geometry to see if that's the case. So beryllium, the central atom, has 2 domains with no lone pairs. So that molecular geometry would be linear, which would look exactly like that. So we were right in that the domains are all the same and the dipoles would cancel, so there would be no net molecular dipole, and the molecule is nonpolar. So we can cancel that out of our list. So this molecule has 32 valence electrons, and I made the Lewis dot structure with all octets around all of the atoms. So now to find the bond dipoles, we're going to look at the electronegativities, and chlorine has a higher electronegativity, so it will have partial negative. And the central atom, carbon, will have a partial positive charge. So the bond dipoles look something like this. So the central atom has 1, 2, 3, 4 domains, indicating that it is a tetrahedral molecular geometry, which would look something like this. And the dipoles would be like this. And in a tetrahedral, all of the domains are the same. So the bond dipoles would cancel, and there would be no net molecular dipole, which means that this molecule is nonpolar. So we can scratch that off our list. So for ozone, it has 18 valence electrons, and I made the Lewis structure with all octets around all the atoms. And once again, there could be two possible Lewis structures. You could take this and put it there, rather than taking those valence electrons and making a double bond there. But for this problem, we're just looking at the Lewis structure and not the actual molecule. So the resonance hybrid doesn't really matter. Also, since the electronegativities are the same for all of these atoms, there's no bond dipoles. So we have to look at the molecular geometry to see if it's polar or nonpolar. Looking at the central O atom, it has 1, 2, 3 domains and 1 lone pair. So its electron domain geometry would be trigonal planar, but its molecular geometry would be bent. So it would look something like this. Looking at the bent molecular geometry, we can see that not all the domains are the same because one's a lone pair, which causes an unequal share of valence electrons. So this would have a partial positive charge, indicating that there would be a net molecular dipole, and the molecule would be polar. So going back to the original problem, the answer would be 2. This one and this one. Now talking about common mistakes, if we had a problem like this, or a molecule like this, if we just found the bond dipoles, we would just think that the two would cancel and the molecule would be nonpolar because it would have no net dipoles. But looking at the molecular geometry, we know it's not true, and there is a molecular dipole pointing down, and the molecule is polar. So you could get the question wrong if you don't look at the molecular geometry.